Welcome to EDU World Space.
Here we don't know the t, the time in the air, and we don't know the initial velocity at the initial angle. The initial angle is 53 degrees, but we don't know the initial velocity at the initial angle. So we have to set up two equations in order to find two unknowns. So let's find the y component first. Delta y equals vy initial times t plus 1/2 a y t squared. So this would be equal to negative 15.0 meters. We choose upwards to be positive. This would be v initial times sine of 53.0 degrees. This would be multiplied by t. This would be minus 4.90 meters per second squared multiplied by t squared. For the x component, we're going to do the exact same thing. However, in the x component, there's acceleration, so the equation actually becomes much simpler. So we have delta x equaling vx initial times t, and again, no acceleration term. So this becomes 40.0 meters. This would be equal to v initial t multiplied by cosine of 53 degrees. And so now we can say that v initial t is going to be equal to 40.0 meters divided by cosine of 53 degrees, or 53.0 degrees. This is equaling 66.47 meters. We're going to use this value to replace v initial t in the y equation here. So once we replace it, we have negative 15.0 meters. This is equaling 66.47 meters multiplied by sine of 53.0 degrees, and then minus again 4.90 meters per second squared times t squared. And to find t squared, now it's actually quite easy. You can just algebraically manipulate directly and then solve for t. So t, after algebraically manipulating, we have t equals 3.727 seconds. So it's in the air for 3.72 seconds, and then we can find v initial quite easily. So v initial would be equal to 40.0 meters divided by t, so 3.727 seconds, multiplied by cosine of 53.0 degrees again. And so v initial is found to be 17.8 meters per second. This would be your initial velocity at that initial angle of 53 degrees. Now, we need to use these values in order to find where essentially they would be if this was only half that. So this would be your answer for part A. For part B, however, the initial velocity is going to be 17.8 meters per second divided by 2. So only half of the initial velocity found in part A. This is equaling 8.9 meters per second. And we can say that this is less than the speed required to make it to the other side. He's going to land in the river, but the question is asking us where will he land? So let's use the y direction, and we have delta y equals v initial y times t plus 1/2 a sub y t squared. This is essentially going to give us negative 100 meters. This would give us 8.9 meters per second multiplied by sine of, again, 53.0 degrees times t, and then this would be minus 4.90 meters per second squared times t squared. As you can see, this is a quadratic equation, and so you can use your TI-84, 85, or 89 in order to solve for t and we see that the only positive root for t is equaling 5.30 seconds. And so now we can say that now we can find the horizontal distance at this time. So delta x, again, there isn't any acceleration in the x direction. So we can simply say 8.9 meters per second multiplied by cosine of 53.0 degrees multiplied by 5.30 seconds. This is going to be equal to 28.4 meters, and this would be 24 meters from launch point. So he would land in the river, specifically 28.4 meters from the initial launch point. This would be our final answer for part B. That is the end of the solution. Thank you for watching.